distortion when you're about a centimeter thick. And so what's the wall thickness of your surface ships? About a centimeter. Two of you said it. I mean, you said it was 0.375. You said it was 3.375 yesterday. I said it was 3/8 of an inch yesterday. Absolutely worst distortion. So they pick that thickness for good reasons, because you know it'll corrode through before you give it to the Coast Guard. Okay, isn't that the reason? Anyway, in any case, it's actually, you know, surface ships have some of the worst distortion going. On the other hand, submarines have some of the highest residual stresses with big plates. And in fact, the Boiler and Pressure Vessel Code requires anything you weld for a pressure vessel has to be stress relieved if it's more than 1.5 inches thick. Okay? Up to about 1 inch, you may only get 80% of the residual stresses. It depends on the weld sequencing and how much other restraint is around it, whether it's the last side on a 6-sided box or whether it's the 4th side on a 6-sided box. You have different amounts of restraint, but you can weld sequence and get around a lot of that, just like John did on controlling those tubes. Okay. Now, what do I want to say about that? So the Boiler Pressure Vessel Code requires that you stress relieve any welds greater than 1.5 inches thick. I won't tell you how thick a submarine hull is, but it is generally thicker than 1.5 inches. So how do you stress relieve a submarine? Or actually, how do you stress relieve boiler and pressure vessels first before we get to submarines?
You anneal them?
You anneal them. You heat them. If you went back to Stout and Doty, that other thing I handed out said stress relief, and it said for A27 steel, desirable 1100 to 1250 degrees Fahrenheit. You put it in a furnace at 1100 to 1250 degrees Fahrenheit for about 1 hour per inch of thickness, so it heats all the way through, and that softens the steel, and the residual stresses will be relieved. Yes?
Does it change
the microstructure?
The steel? I mean, like, the process a lot different for it, right?
You could get reheat cracking that I talked about before, so that when you come down from the stress relief, you have cracks to go along with your stress relief. But if you control the composition of the steel, and we know how to do that now, you don't get reheat cracking. It doesn't really, it actually usually improves properties if you do it properly. Okay? You certainly usually improve toughness, and you improve fatigue resistance. But it's a little pricey, okay, to heat it up like that. And in fact, how do they do it? Maybe that's in my next session. I'm sort of a little bit out of order here. Here it is. How do you do it on big vessels? If you go look up stress relieving, on-site stress relieving on Google, you'll find companies, it used to be called Neuter, it's now called heat treating and stress relief or something. Okay, they got bought out by somebody else. So I got a great big vessel like this. It's going to some oil refinery. You can see they're going to put insulation on it. You have these little lagging studs on the side. So they build themselves a little furnace, and they put it on a little railroad track, and they just put it into the furnace. You build a furnace. Well, you can't always build a furnace, so sometimes they build the furnace around the vessel. So here they're wrapping the whole cylindrical vessel in insulation and heating bars, just like you preheat welds, if you've ever seen that in the shipyard. They do the whole vessel, and they'll heat the whole thing up to 1100 degrees for a couple of days. It can take 2-3 days to do the stress relief. A little pricey, okay? But that's what you have to do to meet the ASME code. And they will stress relieve something the size of this room or bigger, okay? By building the furnace around it. Okay, yeah?
Measure the residual stress.
It's not easy, okay? You can go to Canada and use the CanMet reactor and do neutron diffraction, except you got to bring your sample to Canada, and it's not always that easy to bring a pressure vessel to.
They don't necessarily know that they've reached their goal.
Oh, they know. We know that if you hold at temperature for 1 hour per inch of thickness and soaked it through, and they put thermocouples on there. And we know that if you get it up to that temperature, you will soften it enough that it will relieve its own stresses. That's been well proven, okay?
They're just following the code, whatever the code says they do.
Right.
And then if they follow the code, then they're good.
And there are people who are always trying to sell you some other technology to stress relief. There's something called Bonal, B-O-N-A-L, Technologies in Columbus, Ohio. And for 50 years, they've been trying to tell you they can put all kinds of piezoelectric transducers on there and they can vibrate the vessel at room temperature afterwards and relieve residual stresses. And if you believe that, I got a bridge in Brooklyn that I'd like to sell you, okay? But they're still in business 50 years later. The U.S. Navy spent over $1 million trying to prove whether vibratory stress relief works. They don't use it. So what do you think they concluded? The British Welding Institute spent several $1 million for the oil companies trying to, because if you could do it, it costs us hundreds of millions of dollars to do stress relief every year on these pressure vessels. Okay? You could save a fortune. And because it's the holy grail, let's do something other than heat for stress relief, people are willing to take the chance. And you will sometimes get engineers sign off. We're going to use vibratory stress relief because this salesman told me it works. Okay? Just please tell me which pressure vessel you use vibratory so I can stay away from there. I want to be 10 miles from there. Okay? Because it could fatigue and it has lousy impact properties and it's a problem. Okay? So, other than that, actually, a guy just emailed me 2 weeks ago from an aluminum company, and they're trying to convince this $10 billion a year aluminum company to use vibratory stress relief. He says, "What's your opinion, Tom?" And I told him sort of like I just told you in an email. I said, "But other than that, I think it's great." Okay, I closed it by saying what I'll tell you. I don't think it should be spelled Bonal Technologies. I think it should be B-A-N-A-L Technologies. Okay. But there's snake oil salesmen all around the world, and nothing says they can't live in Columbus. But stress relief is a problem, okay? It's an expensive thing. It's called post-heat. Post-weld heat treatment is a stress relief heat treatment. So someone was asking about what post-heat after class yesterday. And I said, well, we'll get to it. You can preheat the weld to try to have the weld hot so that it drives off the hydrogen with temperature. So you can preheat the weld or you can post-heat the weld. Or some cases, if I got 4340 steel, I probably got to do both. Because I can't let the hydrogen stay in there on a very high hardness steel if it could crack within minutes, okay? If I have, these are the hardness levels, and hydrogen, this is a Tom Eager thing. I've never seen, well actually I have seen, I'll show it to you. If you go to, there's a publication by the British Welding Institute called Welding Steels Without Hydrogen Cracking. You can pass that around, and I should have a copy of it here. In Welding Steels Without Hydrogen Cracking, no, I know I have a copy. Let me borrow yours for just this, okay. There's this plot, and you'll find it in half of these books or more that I just passed around. But Frank Coe, who's probably passed away now, developed this plot in the 1970s when he wrote the first edition of the book. And he has, at the bottom, weld hydrogen milliliters per 100 grams of deposit, so you can think of this as parts per million. I told you about the highest level you might expect in the liquid is like 30 parts per million. If you use rutile electrodes, which is like a 70-14, yeah. No, it's not 70, yeah, 70-14, 70-20, anyway. I gotta go back and look which is rutile, but like a 70-40, 70-14 electrode. I don't have any 70-14s here. You can have very high hydrogen. If you use a basic electrode that's been dried at 100 to 150 C, like this 70-18 that I have, which is not dried, you can have a wide range of moisture in your electrode coating in the flux. Over here they have the weld moisture in, what's it say? Moisture in electrode coating percent by weight. So this would be Well, that's the moisture in the flux coating. Typically, really good electrodes are 0.4. Very, very extra dry electrodes are 0.2. And so you could easily get 5 or 6 parts per million hydrogen in typical mild steel welding. You can use flux cord processes, which can give you very high hydrogen or very low hydrogen, depending on various things. You can use gas shielded welding, where you use argon and CO2, and you can get down very low. Most of the submarine welding, actually most of the shipyard welding now, is either submerged arc or gas shielded welding. We don't use as much stick, but we probably still use it in places that are hard to get to. Well, what does that translate to? A low strength steel, just a 35 KSI yield, which might be a 70 KSI tensile steel, you probably have to have 30 parts per million to crack that. It's very difficult to get hydrogen cracking on a bridge steel or a building steel. You got to really try, and I've tried. I've soaked those electrodes in water and welded with them, and I can't get a hydrogen crack in A36 steel. Okay, maybe if I had higher restraint or something. At 120 KSI, which might be an HSLA 80 or whatever, or an HY 80, it might take 10 parts per million. Well, if I come over here, I ought to be able to use stick electrodes. This one's dying too. I have ordered a new blue one. It quit working. Okay, 10 parts per million. I could use stick electrodes, 70 18s, or actually 80 18s, or actually 110 18s, which is what they typically use in a shipyard, and I can weld HY 80. Okay, HY 100, well, it's going to be in the 5 or 6, and HY 100, I better make sure I really bake those welds. And so if you've been in a shipyard, you know they actually count the number of electrodes. When you go to the stores, at the shipyard, and they will give you 20 electrodes, okay, depending on where you are, because that's what you might be able to weld in the next hour, okay? And when you come back to get another 20 electrodes the next hour, you have to bring the stubs with you, okay? And they count the stubs. If you got 20, if you checked out 20, you got to bring back 20 stubs. If you left a stub out there, they have had pressure vessels in pressure vessel shops blow up because some guy left a 3-inch stub on the ground and some other guy came along 2 days later and welded with it and created a hydrogen crack. And the vessel blew up later. If you're being audited by the ASME code inspectors and they see a stub on the ground, you lose your license. Okay? It's serious. In a Navy shipyard, they count the stubs when you come back to get extra electrodes. And they time you, you can't be out there for 4 hours. Okay? If you get sick, those electrodes go in the trash that you didn't use. Okay? Or they got to go back to the baking oven. They have little hot rod pouches that you can, insulated things that you keep the electrodes in to keep them warm and whatnot. So we do a lot to make sure we have low moisture electrodes. If we have flux shielded electrodes, if we do shielding gas, we make sure the gas is dry. Unless you're a wet welder, you're just full of hydrogen anyway. Okay, but you have to do something. What happened with the Seawolf, they had weld metal that was on the high side chemistry, had enough hardenability. They were at about 150 KSI yield, which would be more like 180 KSI tensile, 2 to 3 parts per million hydrogen, and guess what? You have a hard time achieving that even with the best control in the shipyard. That's why they got hydrogen cracking. They thought they were welding HY 100 and they should have been around here like 130 tensile, but in fact the weld metal was 180 tensile because it had lots of extra alloying. It was on the high side of the chemistry. Okay. The other problem with the Seawolf is, they brought in 6 of us. 2 individuals and 4 companies were brought in by Admiral Firebaugh, who's Chief Engineer of the Navy. Remember, he had designed the Seawolf when he was a captain. And so now they have this huge problem. 18% of the hulls built. It's like 1992 or 91 or something. And they come back and report to them, we got to rip it all out. We're finding these little micro cracks in the weld metal. It wasn't in the heat affected zone. Most of these cracks, hydrogen cracks, occur in the heat affected zone. In fact, they're often called underbead cracks. If you go to the same book on welding steel without hydrogen cracking, they'll show you pictures. And the cracks are in the heat affected zone, and they call them underbead cracks because they don't always penetrate the surface. Pretty bad. You can't even find it with magnetic particle. You could find it with ultrasonics, but in 1992 the Navy hadn't qualified ultrasonics for the shipyard. And they look like this. Okay, this one is a toe crack, actually did penetrate the surface. But in any case, these are underbead cracks, and it's a problem. Well, it turns out the way they discovered it, it turns out in the weld metal, instead of having long cracks that might be 1/4 of an inch or 1/2 an inch long, everything in shipyards is designed to look for 1/8 inch cracks or larger, because the probability of detection is reasonably good if you have an 1/8 inch crack. The Air Force has done all kinds of studies on non-destructive testing, and they can find with greater than 90% probability, they'll find things that are greater than 1/8 of an inch in size. These things were 1/16 of an inch in size in the weld metal. And they were all through it, because the weld metal had a finer structure. And the way they discovered it, they've been doing their tests and their radiography, but none of the tests were designed to find cracks that small. A grinder was grinding the outside hull of the ship. You know anything about submarines? You don't even like to have weld reinforcement on the outside because it causes ripples in the water, which with sonar you can find. Makes more noise than a whale, I guess. Whatever it does, probably makes less noise than who knows. And so the guy was grinding the weld smooth, and he happened to notice that the grinding swarf, you know, the little powder, we call it swarf, is very good if you play Scrabble, S-W-A-R-F, good Scrabble word. Not a lot of your compatriots will know what it means, but he noticed the swarf was actually aligning in these little 1/16 inch. He was doing a magnetic particle test with the grinding swarf, okay? He was making magnetite, you know, out of steel, and it was lining up. And he said, I've never seen that before. So he asked some engineer, oh, have you ever seen anything like this? They said, no. And they went and they did a more complete, more sensitive test. The whole hull, 18%, was riddled with these little cracks. And the decision was to rip it out. So turns out they hired 2 individuals, myself and a guy who had helped invent gas metal arc welding. He used to be at Airco, which is now part of Lincoln Electric. And they hired Lincoln Electric as a company and a couple of other companies, 4 companies. And we were supposed to advise Admiral Firebaugh and his staff on what was Electric Boat doing the right things to fix this, okay? Well, the other individual talked to the press. We were told, don't talk to the press. Well, he talked to the press, so he was booted out. So there are only 5 of us left. We actually had to write a report. I wrote a report, and there was almost no data. It's a little bit of data. They had measured hydrogen. I noticed, I plotted, they were using 3 different diameter welding wires. I can't remember, like it was 3/32, 1/8 inch, and what's in between here? No, that's not, they weren't using 3/30. They were doing 3/16. No, they weren't doing 3/16. It was like 3/32, 1/8 inch, and I don't remember. Let's just say the other was 16th. Okay, I don't remember what it was, depending on the thickness of what they were doing. And they had hydrogen content. They'd done all kinds of hydrogen tests, and I plotted this, and I found the highest hydrogen in the welds, or the wires. They actually measured on the wires. Okay, they tested the wires for hydrogen because there'll be some residual hydrogen. This was highest. This was next highest, and this was the least hydrogen. And so, what was the conclusion? That's the data I had. And there was a range. These ranges actually overlapped if you looked at all the individual measurements they had made. Can anyone guess what my conclusion was? Pardon me? Well, we knew it was hydrogen cracking, okay? My conclusion was it was dirty wire. Okay, this is milliliters of hydrogen per 100 grams of weld, rutile electrodes, high hydrogen, basic which is 7018, that's what they're trying to weld with. Dirty wire can give you regions higher hydrogen than you would like to see in 180 KSI weld metal, clean, dry, flux and wire, et cetera, okay? Now, why would they have dirty wire as a function of diameter? Which one has the highest surface to volume ratio? Surface to volume goes as 1 over r, right? Pi r squared versus, you know, well, pi d versus pi, yeah, 2 pi r versus, no, it's a cylinder, so pi d versus pi r squared. Yeah, the volume goes as pi r squared. So surface to volume, the volume goes pi r squared times L, and the surface goes as 2 pi r times L. I mean, this is not real sophisticated stuff, but nonetheless, and you do this, everything's proportional to 1 over r. Okay, smaller diameter wire, more surface to volume. So dirty wire has more surface, and what's on the surface? Drawing lubricant. They had to draw that wire, and they had to use a lubricant, which is made of grease. And so when I wrote my report, this was my conclusion. And I was told by one of the captains, actually I had to meet with 2 captains, okay? And they introduced them to me, I can't remember their names. They said, he owns the boats and he operates them, okay, for all the submarines, okay? And what they wanted to know, well, I'll tell you what they wanted to know, but in a second. But they told me, they said, yours was the only report that said anything. Okay, gave us any conclusion. Everyone else just sort of spit back well, this is the data we saw. Well, the Navy could tell the data. That was their data. It was Electric Boat's data. They had that. But I actually drew a conclusion. I analyzed the data and drew a conclusion that this could have been dirty welding wire. Lincoln Electric was not happy that I was impugning their wire and their cleaning procedures. But since we weren't all supposed to know what other people's conclusions were, they didn't know it was me. Okay, I don't think they did. They may have found out. But anyway, but the question they asked me, which was sort of an interesting question, was, okay, we have the Seawolf and we're going to rebuild that, but we have 2 ships out there that we've already built with an HY100 section. In order to prepare and not just go hog wild, let's throw titanium piping into these, what, LPDs or whatever you call them, right? They actually took baby steps in the submarine army, or Navy, sorry, Army, Navy, whatever it is. They basically took baby steps, and in some of the prior, what was it, 688 class? I don't remember, okay? Some of the prior attack subs, rather than building an HY80, they used same thickness and everything, but they put in HY100, which was what they were building the Seawolf out of, okay? Just to get the experience and see if they would have any fabrication problems with the HY100 as opposed to the HY80. So they built, you know, like a 20 or 30 or 40 foot long section, I don't know. And they said, we got a couple of subs out there that have HY100 in them in the hull. What should we do? Do we have to derate them? Okay. And my answer was, actually is what they wanted to hear. They actually wanted the truth. But the truth was, no, you don't have to derate them. You may have to do a little more inspection when they come back for port for inspections, but those little 1/16 of an inch long cracks, how fast are they going to grow? Okay? They're starting right down here, and they got plenty of time, okay, between inspections, between overhauls, okay? So, yeah, when they come back, you know, increase your inspection budget on those welds and see if you're getting, if the cracks are growing. You probably can't even find the cracks, okay, for 10 or 20 years if they were. And they may even go the whole life of the ship till you put it, you put it in mothballs or send it. You don't send those to Bangladesh, do you? Okay. But in any case, actually, you used to blow them up off Newport News or Nag's Head. You know that story, right? Oh, that's actually sort of the story in Hunt for Red October. Was it the Patrick Henry? No, I can't remember if it's the Patrick Henry. But they used to scuttle them and just bury them in the ocean with the reactor too. That was before some people decided that wasn't a good thing to do. In any case, if you went through fracture, I had to explain fracture mechanics to these two captains, and that you don't have to worry about it. You don't have to derate them, but you might want to increase your inspection budget in the shipyard, okay? Because those cracks could not grow fast enough. Did you know that virtually every airplane that's flying is full of cracks? There's a story about the Air Force wanted to do a acoustic emission test, put an acoustic emission monitor on an aircraft, and they were going to introduce a flaw, a crack, into one of the structures, and they wanted to see if the acoustic emission could pick this up as part of a research project. And since they were going to introduce a crack, that would make the plane unairworthy, and they had to get a general to sign off on it, that they could fly an airplane with a crack in it. And he refused to fly, to sign off. I'm not going to fly any airplane with a crack in it. Excuse me, General, but every one of them out there has a crack in it, and you just don't know where they are. This one, at least we know where it is, and we're going to monitor it. They had to fly it on an Australian jet. Okay, because this Air Force general, I'm not going to fly any airplanes with cracks. Okay. We have cracks all through planes and submarines and other places. You know that. You've been telling me about it in your presentations. Not cracks, great big holes and everything. It all sort of, steel is a very forgiving material. So they didn't have to derate it so far as that goes, but it did cost a lot of money, and Congress wasn't very happy, and there's other stories that follow on for the next 10 years from that. But getting back to wherever I was, we were talking about how do you stress relieve a submarine. It's got a wall thickness. It says it's going to have yield level residual stresses, and you don't like residual stresses because they can run into fatigue cracks and everything else, poor toughness. We do stress relieve submarines. Does anyone know how we stress relieve the submarine? We don't stick the whole thing in an oven.
I mean, you just run, something on a tractor that goes around heating it.
Nope, we don't do that either. Because if you do that, you're going to have a region between the cold and the hot that's in this region where we have all kinds of temper embrittlement and other things, which would just destroy the properties of that part of the steel in the heat affected zone of the heat treatment. So local stress relief has to be done. We do local stress relief sometimes. So that's a good thought, but that's not what we do on submarines. Not every type of stress relief is thermal. I can do mechanical stress relief, okay? Every aircraft wing on every Boeing or anyone else's jet, when they make the aluminum plate in Davenport, Iowa, could be 4-inch, 6-inch thick plate, and they quench it and heat treat it to get high strength. They have terrible residual stresses in that. And if you made that wing out of that material with those residual stresses, it would fatigue within hundreds of hours of operation. So they obviously don't do that. How do they stress relieve it? I've been to the room. It wasn't an operation, but they take that whole plate that could be 50 feet long and it could be 4 inches thick, and they have this, I can't remember if it was 3 million or 10 million pound machine, great hydraulic jaws, and they grab it and they stretch it 3%. They plastically deform it, and that relieves the residual stresses. And so many of your aluminum alloys are stress relieved by adding mechanical stretching plasticity. When does a submarine see plasticity in its welds?
Deep dive.
The very first deep dive. And who gets to go on that dive?
Billions.
Yeah.
All the management of the shipyard. Okay? One of the best quality control techniques I've ever heard is you send the managers on the first deep dive. Okay? They have to go. Not all of them, but most of them. And I don't know if they draw straws to see who takes the chance, but they have real incentive to make sure in the submarine shipyard that they do good quality control, at least on the hull welds, okay? Because they get to go on the first deep dive. And on that first deep dive, you mechanically stress relieve the welds. So they do stress relieve them. It might be a long story, but it sort of tells you a lot of principles about stress relief and management. There actually are some morals to these stories. You may have to hunt for them, but they're there somewhere. Okay, why don't we take a break come back at 8:45. In the meantime, I got to find you the plot of hydrogen and wells. Oh, that's the one in Kentucky. No wonder I couldn't find it. I was looking at the wrong book.
So like every morning make myself an omelet and something. But I'm pretty good. Stop making my breakfast.
So a couple of you guys are welders. How much of this stuff did you already know about steel?
Not much to the fidelity, but I know a little bit about steel and hydrogen-induced cracking, just because that was something that we were very interested in.
Yeah, but you didn't all know all the scientific reasons or the principles behind it,
I
right?
had tried to read portions of Coe's book, but most of it was over my head.
Yeah.
I have Easterling too. I just read selected sections, trying to understand.
I have 2 copies of Easterling. It's out of print,
I have one too.
and it's like $180 or something. If you go look on Amazon, you can buy a used copy, but it's pretty pricey. It's actually a pretty good book, but it helps if you're already a metallurgist. Okay, I mean, no, I understand that these things, and sometimes I feel like I'm talking, particularly if I have, you know, the 2 of you that are welders, I feel like I'm talking down to you, but I guess I'm not really. Okay.
Don't worry about that.
Pardon me? Oh. Okay. But yeah, actually, I was wondering, do you actually, how much welding do you do? I mean, you're actually the supervisor of the divers.
The Navy in general does 0 welding. Navy divers don't weld, except in very specific cases, and that's only really for practice. We contract it. It's too
But you
expensive.
contract it to certified welders.
It's too
Yeah.
expensive to maintain qualified underwater welding systems.
Yeah, okay, yep. Well, expensive.
That's the way
Oh,
the Navy guys rotate through their commands.
Yeah.
There's no way to develop any sort of proficiency.
Well, one of the ways I learned failure analysis was when I came back in 1976 from Bethlehem Steel. I had to take a 1/3 cut in pay, okay, to be a faculty member. And at that point, I had 3 children, maybe a 4th. By the time I bought my house in '78, and I had to buy it because my mother-in-law couldn't live alone anymore, and we had to move her in. She lived with us for 17 years, but I couldn't afford my house. And I never knew where the mortgage payment was coming more than 2 months ahead. And I had to rely on some consulting to do this. And I did have one consulting contract with the gold company down south of here in Attleboro. But I was still looking for a little more, and I didn't have much then. And a guy down south of here, Bruce Sylvester, his father had worked for Factory Mutual and as a metallurgist, and then had left Factory Mutual Research to start his own consulting firm, which did non-destructive testing. They had, his chemist was the guy who used to do chemical analyses when the Navy had a Navy shipyard here in Boston, and that guy, when they closed the shipyard, went to work for Sylvester and J.G. Sylvester and Associates. Well, J.G. Sylvester was a pretty good metallurgist, so far as I can tell, but he died in like when he was about 50, just had a heart attack and died. And he left the business to his sons. His wife owned it. So their mother owned the business. And I guess the Sylvester sons, the three of them, one of them had a couple of years of college or something. That was probably Bruce. The others may have graduated from high school, but these guys were not rocket scientists, okay? But Bruce wanted to get into the diving business. He loved to dive. And they were doing, magnetic particle and X-rays, and this is the facility of their father. And he wanted to get into two areas. He wanted to get in doing nuclear work, failure analysis on nuclear stuff, and he also wanted to get into diving business. And he actually bartered for Mass Tank, which builds a lot of storage tanks and stuff. They built him a 10-foot high diving tank, okay, that was like 20 feet diameter. It was in the back of their facility. And so they had all this diving equipment, and they kind of designed their own ultrasonic stuff for underwater and stuff because they didn't want to buy the commercial stuff. It's too expensive, so they kind of made up their own stuff. Well, Bruce was really trying to push for this, and we didn't know it, but what had happened, the reason Bruce was looking for a metallurgist, and he had moved another guy up to office manager, this guy Ken Baker had been his office manager, and his metallurgist had been a guy, David Holt, who had taught me. Dave Holt had been a junior faculty member here, didn't get tenure, and decided to go into the ministry when he didn't get tenure at MIT. He was working for $10 an hour doing the metallurgical failure analysis for Sylvester. None of us knew it until about 3 years later, but Bruce Sylvester was making fake invoices, submitting them to the bank to get loans from the bank based on his accounts receivables, but this was for work that never existed. Finally, about 1983, they caught up with Bruce. The bank caught up with him. Bruce sort of disappeared. His mother was stuck having to mortgage her home. Bruce had embezzled $500,000 from his mother.
Real stand-up guy.
Yeah, well, he was. Well, Sylvester still existed.